do anything here. This chapter is between my daughter being sick and then the snow days and everything else that I've barely seen you guys. Do you guys want to start with some questions on stuff? What do you guys... This is supposed to be the review day. I don't know really what we need at this point because I've seen so little of you guys. Seems like the homework quizzes and stuff have been going well. So that's a good sign. You guys, do we have questions from homeworks or anything, or? Yeah, Elena.
Number 27
5.3, number 27. Okay. All right. So it's tempting to want to do like this, right? And try to like push that integral onto both parentheses. Cannot do that. That's not a thing we can do. And we don't have any integration rules for a product. So really what you'd want to do here is you'd want to start by foiling that guy out. And once that's foiled out, we can then just integrate term by term. So the antiderivative of u squared minus the antiderivative of u minus the antiderivative of 6. Does that feel okay, Elena? Okay. And then if we evaluate that, and then we just simplify by hand or whatever here. So it's like 1/3 minus 1/2 minus 6. So if we make a common denominator, that's 2/6 minus 3/6 minus 36/6. So that's going to be negative 37/6. It's hard to say. Is that okay? I'm sorry, you said whatever you said was very quiet and I couldn't hear it. Combine, what do you, I'm sorry, no, it was just quiet, I just couldn't hear. You're okay? I'm sorry. Apparently I'm very deaf today. Others, questions from homework. Happy to do more. Yeah, Paulo.
It was 5.5. It was a pink question. It was like displacement and like arc length.
Displacement and arc length, huh?
67.
On 5.5?
Yes.
Okay. 67. So this is what I have for 67 and 5.5.
Yeah.
Okay. So here, what's up? Okay.
Never mind, I apologize.
No, you're fine. 67 and 5.4 is talking about marginal costs for manufacturing.
Oh no, it's 55.
55. So it says in
59.
59. Okay. So the velocity function, et cetera, et cetera. Okay. Okay, well, let's do that then. If anybody wants, we can come back and do 67 if you're like, ooh, that was a good one. But we aim to please. All right, so the velocity function given in meters per second for a particle moving along a line. Find the displacement A and then the distance traveled during the given time. Okay, so if we're looking for displacement, that's just going to be the integral of the velocity over the given time interval. If I want the distance, that's going to be the integral of the absolute value of the velocity function over the given interval. Okay? Because we need to make sure that we're counting, if we're counting distance, if something goes like back and forth and then continues on, you need to count like all those back and forth trips where displacement doesn't catch that. Feel okay?
Yeah.
Okay. So here, if we go so to integrate this, we can just integrate term by term. Should be pretty easy to integrate this. The antiderivative of 3t is just going to be 3t squared over 2. The antiderivative of 5 is just going to be 5t. And then we evaluate from 0 to 3. So that's 27 over 2 minus 20 or minus 15, or let's say 30 over 2. So the displacement there is like negative 3 over 2, and this should be meters. Does that feel okay? Okay. So same problem, except now we have a absolute value around this. So what I need to do is I need to take this absolute value function and try to rewrite it as a piecewise, right? So for some chunk of this, it's just going to act like 3t minus 5. And then for the other chunk of it, it's going to act like negative of 3t minus 5. So what we need to do is figure out when this thing crosses from being positive to negative, right? So that's exactly where 3t minus 5 crosses the x-axis. So if I solve that, I get 5/3. So if we are greater than or equal to 5/3, we'll do the top one. If we're less than 5/3, we'll do the bottom. And it doesn't matter which one you stick the or equal to on, whether it goes on the greater or the less than, it doesn't make any difference. Still the same function. So far, so good? Okay. So what we'll do then is we're going to break up this integral into two chunks. We're going to go 0 to 5/3, we're going to be integrate integrating the negative chunk. And then from 5/3 to 3, we're going to integrate the positive chunk. Is that okay? Yes, because I know that for t less than 5/3, it's the negative one. So from 0 to 5/3, I need the negative piece, right? And then from t greater than 5/3, I need the positive piece. So from 5/3 to 3, gets the positive piece. So it's not negative first then positive. It's dictated by the piecewise function on which piece you need to be needs to be positive or negative. Does that make sense?
Yeah.
Okay. Still doing good? Okay. So the antiderivatives of these are easy. We've already done them. So I'm just going to kind of copy those in. Oops. So far, so good? Okay. And now we just need to go ahead and do that. So plug those guys in. That'll be positive now. So I went ahead and distributed the negative sign through when I did that. And then minus 0 plus, oops, should be not 1/2, 3/2. And I'm going to distribute the negative sign through here. Does that all look okay?
Yeah.
So if I don't have a calculator to do this, I'm going to notice that, hey, those two guys are like terms. I can just combine those together and think about it that way. And these guys are like terms. So I can just like add those together also. And then I just got these other two guys here floating around at the end. So that's just going to make the arithmetic a little bit simpler. So that's going to be negative 25 over 3 plus 50 over 3 plus 27 over 2 minus 15. And we just make a common denominator here. So negative 50 over 6 plus 100 over 6 plus, 3 times 21, 81 over 6 minus 90 over 6. And let's see, so that makes like 10 over 6. So 91 minus 50, so 41 over 6 meters, something like that.
Yeah, that makes sense. I just didn't know about the absolute value.
Yeah, so that's the difference between displacement and distance. So displacement is just the integral of the velocity function. Our distance is the absolute value of the velocity function. And then you have to break the integral into at least two pieces, you know. But yeah, that's the gist of it. Yep. And again, if you have a calculator to do that, you could just look at the calculator and see where the graph is of the absolute value is like below the x-axis and where it's above. Yeah.
At the top, to get the 5/3, like 2 to 3,
Where did you get the 3 from?
So the original problem was
Oh.
0 to 3. So that's where the 3 is just left over from the original. So I broke it into 0 to 5/3 and then 5/3 to 3 because it was originally just 0 to 3. Violet.
67.
Oh, sure. So this is a integration by parts problem. U substitution problem. So when I see an integral that looks like the composition of two functions, right? Like this is x minus 1 composed with the square root of x. If I were to try to differentiate that, that's a chain rule differentiation problem. Everybody kind of recognize that? The U substitution is my antiderivative technique for undoing a chain rule problem. So what I do is I'm going to start with the inner piece of that composition of two functions, and I'm going to let that be the value u. And then I'm going to take the derivative of both sides with respect to x. So the derivative of u with respect to x is going to be du dx. And then the derivative of x with respect to x is 1. And the derivative of 1 is 0, so I'm not going to bother to write that. Now I'm going to treat this kind of like a fraction and multiply dx to both sides. And I have that du is equal to 1 dx. So now if I am almost ready to make a substitution, right? To get an integral with just u's in it. So I have that piece is a u, right? And this piece is going to be a du. But what about this guy? This is the trickiest type of u substitution problem. When we have like, I go and I declare my u, I do my derivative, and I try to substitute everything back in, but I still have an x remaining, or x's remaining. So what I'm going to do is I'm going to use this statement, because if I add 1 to both sides, I can say that x is the same thing as u plus 1. And now I have the final piece. So if I go ahead and rewrite this now, I have the integral of u plus 1 times the square root of u du. Everybody's okay with this? And if I think about this u, or the square root of u, as just u to the 1/2, I can distribute this in, and then it's like an easy antiderivative rule. So that's going to give me u to the 5/2 times 2/5 plus u to the 3/2 times 2/3. Everybody's okay? So that's like the indefinite integral version. Now, if I'm doing this problem as a definite integral problem, so I have like two options here on how I want to deal with this. I can continue on and just put in my x back in here. Right? Because I know that, And this was evaluated from like 0 to 1 to 2. Yeah, of course. So you could do it that way. Or the other option, and it doesn't make any difference. There's like, it's just a matter of like a question of preference. Or you can reset your integral bounds so that they're in terms of u. So for x's, we went from 1 to 2. For u's, I know that u is equal to x minus 1. So I'd take 1 minus 1 to get 0, and then 2 minus 1 to get 1. So it doesn't matter which way you want to do this, whether you want to reset your bounds of integration in terms of u and not substitute. So that would allow me to just take this and evaluate it from 0 to 1 without putting the x's back in. Or I can put the x's back in and keep the old bounds of integration. You will get the same answer either way. I typically think that rewriting the bounds in terms of u tends to make the arithmetic easier. If it's a no calculator situation, I think that's typically makes the number crunch at the end a little bit easier. Like this one is now a piece of cake. If I'm going from 1 to 0, I'm just going to end up with 2/5 minus or plus 2/3. And that's easy to handle. If I do it the other way, it's like, if I leave the x's, it's just messier, right? So resetting the bounds, if you have no calculator, is often cleaner, but it doesn't matter. You can do it either way. You'll get the same result. Violet, does that feel okay? And I'll tell you this, that I will have on your test, there will be an integral where you have to use this trick where you have like a leftover x that doesn't sub out immediately with just your basic u substitution, where you have to come back and make that second substitution. So this was a nice example question to have spoken about, because I would have wanted to come back and do an example like this anyway, because it's a nice trick and it's one that's like not always obvious that, oh yeah, I can just take that original substitution, rearrange it a little bit and drop it in, and that takes care of that x that I couldn't seem to get rid of. Finn. Yeah, absolutely. Okay. So if we look at this one, it's a little, I mean, it's obvious that we don't have an antiderivative rule to go directly for this, right? And maybe it's not even entirely obvious like what the u should be in looking at this. You might think let's use that 1 minus x squared, since it's the inner part of the composition, but how are we going to get rid of the sine inverse of x? Because that has to get subbed out to be u of something also. So what I noticed when I looked at this is I remember that my derivative rules, that the derivative of sine inverse is that. So I would pick the u to be sine inverse of x, because when I do the derivative of that, du dx is 1 over the square root of 1 minus x squared. So I can just say that du is equal to that, and then like times the dx at the end. So that's the substitution that you need to make here. Is that, you see how I came up with that? So again, like if you look at it, maybe it's not obvious what the inner chunk, or you pick the inner chunk and it's just not working out for you. It's like, oh, this is not, go back and look and maybe there's like an obvious, oh, look, this whole big thing is just the derivative of that piece. That can happen. So keep in mind those, like, you're looking to substitute everything out. All right. So that looks good. So let's also change our bounds. I'm going to do it that way because that's the way I prefer to do it. So if I do like u of 0, that's like sine inverse of 0, which is just 0, right? And if I do u of 1/2, that's sine inverse of 1/2, which is it pi over 6 or pi over 3? So this is the way I think about it, right? If I'm on the unit circle and say that's 1 and that's like 1/2, that's my y coordinate, right? And this is like so I'm drawing a, like, so that's that, right? If the x was 1/2, it would be the bigger angle, right? So between the 30 and the 60, which angle has the y coordinate 1/2? The smaller of them, right? Which is the 30-degree angle, which is the pi over 6. Again, maybe I don't have it memorized, but if I know how the unit circle works, I can kind of draw myself a picture and reason that out pretty quickly, even if I don't have a calculator, even if I don't have it memorized. I remember that x is cosine and y is sine, and I can sketch enough of a picture to figure out, like, I know it's going to be one of these 30, 60, or 45 multiples. Easy enough for me to kind of reason that out, even if I don't have it memorized. Does that feel okay? All right. So if we substitute this all in now, we have all this mess written down. So we have the integral now from 0 to pi over 6 of u du. Right? So again, the u was my sine inverse, and then like my du was all of that stuff, right? So it turns into a really easy integral here. And because we've already done the use or the changed our bounds, we don't even have to plug the x's back in. So that's going to be, what, pi squared over 72 or something? So like once you've got the u sub done, that's the hard part. Usually the integral you're left with should be really easy. Does that feel okay, Finn? Okay. You guys followed kind of my reasoning on that. Tried to really explain through. I know you haven't seen that much of me here in the last 2 weeks, really. Ugh. Sorry. But that's a pretty standard level u sub problem. Again, you didn't have to change the bounds like we did. That's the way I prefer to do it. I think it makes, if I'm trying to do this without a calculator, way simpler. Just makes the arithmetic at the end less messy And if I don't have a calculator, I'm very interested in making my arithmetic less messy. And since there's sections on the AP exam where there's no calculators, there's sections on your test with no calculator, I think it's really important that you're able to do this method of changing replacing the bounds when you do that U substitution to make your life easier. But you can still do it if you don't, right? Still possible. I think it's a little more time consuming and can get a little messy, but it's not like it's intractable or something. Paulo?
For the test, we have to like solve integrals.
Right. So yeah. So yes, there'll be times where you have to do U sub on it, and there's times where you shouldn't, where it's just like I can just use my basic antiderivative rules and get through this. So like if we went back to this one that Elaine had asked about, this is one where you wouldn't want to do a U sub on it. It's going to make life worse trying to do that. All you need to do is like FOIL it out and then it's ready to be done the way it is. Like no problem. As opposed to this one where there's no antiderivative rule for a product like that. Could I write that x as like the square root of x squared and then FOIL it in? Yeah, but then you still have the antiderivative of composition, which we don't have a way to do either. So it's like there's not really any way to do that without like doing some illegal algebra things to get to a form where you can do the antiderivative on it. Had to be U subbed. You can kind of see the difference? So usually it's pretty obvious after you look at it for a minute that like, okay, I don't have an antiderivative rule to do this. There's no like algebraic rearrangement that can get me to a point where I can just do a basic antiderivative rule on it. Probably has to be a U sub problem. Does that feel okay? Nate?
So like for U sub, you got like a function inside of the square root.
So typically that's what you'd want to do. What you want to do is you want to pick the inner function. So that'll depend a little bit. Like here, say for number 69, I would pick the natural log of x as my u because I know that the derivative of that is 1 over x. So I'm going to pick up that stuff, and that gets me all the x's with my substitution. I should be smooth sailing. If I look at, like this one, I have e to the z's. I would pick the denominator as my u because I know the derivative of that is going to be e to the z and then plus 1, which is my numerator. So you have to look at it a little bit, but you're looking for, okay, what chunk, if I take the derivative of it, can I get rid of everything else? Oftentimes that's going to be the innermost thing, but it doesn't always. Like in 70 with the one that Finn asked about, you wouldn't want to pick 1 minus x squared as your u because there's no way that the derivative of that is going to get rid of the sine inverse, right? You won't be able to substitute that away. Does that make sense, Nate?
Yeah. So then what do you do with the other function, the problem?
So if we were doing like 69, we say u is the natural log of x. So du is 1 over x dx. So when I do the substitution, I'm going to have 1 over square root of u and then du. Right? Because the u is just going into that. Do you see what I'm saying? and just running out of space here. So if I go over here, when I look at this problem, I see 1 over the square root of ln x times 1 over x times dx. So like the u is going in there. This stuff is the du. So I'm left with just the integral of 1 over the square root of u du.
Oh.
And then I can just rewrite that as like u to the negative 1/2 and antiderivative rule that. Is that, you see it now? So like oftentimes in my head, I'm taking that, something that's a fraction like that, and just kind of breaking it into like little products. Oftentimes that'll, yeah, so oftentimes that's a really effective, if you're not even sure what to do, like how can I like chunk this so it's not just like one big thing. I can like, okay, what are the pieces that I kind of need to fiddle around with to fit together? Does that feel better? Okay. Should we talk about test format here? I think we talked about this once already, but it's probably worth doing it again, right? So the first section is a no calculator section. You have 7 multiple choice and 1 FRQ. The FRQ will be similar in style to those 5.3 practice pack problems that I gave you guys. And I think I went and put in my, yeah, I did. Okay, so I went and put in my worked out solutions for all these also, so you can see, you know, maybe in more detail what Mr. Kulik did than if I just put in the AP's answer keys, which are sometimes like a little bit difficult to read. So I thought that would be helpful. So I did that. The second part is a calculator section. So you have 3 MCQs, and then you have 7 integral problems. In those 7 integration problems, all mixed up, you're going to have indefinite integrals, definite integrals, u sub, etc. They're all going to just be mixed up. So it's not going to be like integrate this by u sub, integrate this. I'm going to count on you guys being able to recognize the case. That's half the battle. Yeah, Nate?
Indefinite is the one where like there's no balance.
Correct. So you're just giving the general antiderivative. So it needs to have what at the end? Plus c. Excellent.
Definite has the balance, right?
Yes, correct. 100%. And then I have 1 free response question that's like a Riemann sum problem. So I'll be asking you to calculate a bunch of Riemann sums or something. Does that feel okay? Notice that the single biggest section is, you know, being able to actually just do integrals. They'll all be like algebraic. So it'll be just, you know, it'll be like these problems that we were just kind of looking at. You know, like this 61 through 72 or this 19 through 42. But there'll be indefinite ones mixed in. I think these all look like definite integrals also, but there'll be indefinite ones mixed in there. But it'll just look like that, just algebraic. All the other different forms or different ways you might have to integrate something if you're given something other than a function are handled in multiple choice. Right? So like if you're given a graph instead of a function, you can still do the integral just by looking at the area under the curve. So usually you're using geometry to just like break it up into rectangles and triangles and circles and stuff like that, add that stuff up, or subtract it if it's below. Mm-hmm. Let's look at these guys. So two is a good one. right? Like that's a good one to make sure that you're able to do. Because we know that the integral from 2 to 4 of f of x dx is just g of 4 minus g of 2. So then you can just rearrange that to get the g of 4 by itself. Right, and just add g of 2 to both sides. And we know g of 2 is negative 7, so. Right, so that's a good one. That's like just a fundamental theorem of calculus part 2 kind of problem. These are good ones. Where you can write, where you can, have to piece this together from the different pieces. So we know like the integral from negative 10 to 4 of g of x is going to be like the integral from negative 10 to 6. And then minus the integral from 6 to 4. Like you just piece it together or whatever using your integration rules. Actually, I would probably just do that, and then those two add to give you this thing. Because now the bounds match in the right places. That's the easiest way of looking at that. But that type of problem is really classic. Guarantee you'll see something like that in MCQs. Sure. So we have for definite integrals, if you have values a, b, and c, if I have the integral from a to c of f of x dx, I can rewrite that from a to b f of x dx plus b to c f of x dx. Right, that's exactly what we did to do the absolute value integral earlier. Right, we just used that. So that's what I'm going to be doing here. So I want to build this integral from 4 to negative 10 because I know that's equal to 3. So what I want to do is let's actually switch these ones. So I know like integral from 4 to negative 10 g of x dx is going to equal the integral from 4 to 6 g of x dx plus the integral from 6 to negative 10 g of x dx. Right? And I know that this one is negative 3, this one is 5. So I know the integral from 6 to negative 10 g of x dx is going to equal negative 8. But notice that these bounds are flipped in the problem. It's asking us for this integral. So then I just, it's 8. Does that make sense, Paulo?
Yeah.
Yeah. So I just about like piecing them together back using those rules. So those are the most common ones you'll get is to flip the bounds, you make it negative, and then you can add things together as long as like their bounds match upper to lower. But that's a classic example. Guaranteed you'll have something in that type. Let's find another good one. So this is the same type of problem here, just another example. Just a little bit harder because now they have this thing that you have to piece that stuff together to make, but It's fine. I'm looking for something specific. Let's. Yeah, so this is a good one. This is another classic example. So it says if f is defined by the function f of x equals the square root of x cubed plus 2, and g is an antiderivative of f such that g of 3 equals 5, then what is g of 1? So whenever you see something like this, you should be thinking fundamental theorem of calculus part 2. So we can say that, right? And we know that g of 3 is 5. So if we knew what this was, we could just solve for g of 1, right? Now, take a look at that integral. Can you do that by hand? Do we have an antiderivative rule to handle that? I don't know one. Is there a u sub rule that's going to handle that? Can I u sub that? No, because the obvious u would be x cubed plus 2, but if I try to take the derivative of that, I don't have an extra x squared floating around anywhere. So how am I supposed to do that? Yes! Yeah, notice this is a calculator problem. The only way to handle this is to just plug this into your calculator and get the answer. It's exactly what they want you to do. So again, to remind you how to do this on your calculator, you press the math button, you scroll down to the bottom till you find the fnint command, and then you just enter it into your calculator just like it looks like on your sheet of paper. So that's what that integral is. So then we just subtract 5 from both sides and then divide by -1. And that should be our answer for g of 1. Because of that. Because there's a negative sign in front of the g1. That's fine. So it would be answer would be B. Does that look okay? Very classic AP question where they're checking to make sure that you recognize that, like, my calculator can just do this integral. They want you to do that. In particular, as we get deeper in, especially on the FRQs, it's going to be, questions will be like, set up the integral but do not solve. Or, you know, like you set up an integral that you cannot do by hand. It's a calculator only kind of problem. And they know that, but they want you to use your calculator to do it. Or it's going to be something that's like, ugh, this is just going to take forever to do by hand. They don't want you to do that. They want you to use your calculator if it's a calculator FRQ. But that's like a classic. You know, it's the same idea as that number 2. It's just like, this is the calculator version of number 2, right? All right. You know, actually, in looking at this, like, number 3 is a pretty good problem also. So if we're looking for a max or min, what do we need to take? We need to do the derivative and look where it's equal to 0. We need to look at those critical values. So the derivative is going to cancel out the integral, right? But it's also going to give me, because my bound is not just regular x, it's a function, it's a chain rule problem. So that's my first derivative. If I set that equal to 0 and solve, even without a calculator, I recognize this thing is always positive. Right? If I have an exponential function, it can't ever become negative because I'm taking a positive number and raising it to a power. It's never going to give me a negative value, can't ever cross, or can't even give me 0. It can't cross the x-axis at all. So the only possibility is just x equals 3 over 2. And I know that for values less than 3 over 2, we were positive. No. For values less than 3 over 2, so like 1/2, it's going to be negative. And then values bigger than 3 over 2, you're going to be positive, which is exactly what we'd expect at a minimum. So I need to make sure I check this, though, because one of the answers is there is no minimum. So even though I got 3 over 2 as the only critical point, that's great, but it might not be a minimum. It might be a maximum. Have to check that, since one of the options is there is no minimum. Ugh. Does that feel okay? And again, I can tell it's negative just by plugging, like, if I plug 1 into that, 2 minus 3 is negative 1. This is always positive, so the derivative is negative there. If I plug something bigger like 2 in, 2 times 2 is 4 minus 3 is positive 1 times another positive is positive. So I'm able to check that really quickly, since it's essentially the only piece that matters is the linear piece in there. That's nice, but it's not more complicated. But maybe not totally obvious that the e to the x squared doesn't really matter to us. But you could look at it in your calculator too, but I don't think you actually need a calculator to do that problem. Does that feel okay? Like you could have graphed this and looked at the picture, and that would have been pretty simple to do as well after you did the derivative. So again, like the MCQs, I've given you some hints about like types that you might see again. That's awfully nice, Mr. Kulik. Thank you. Right? So I can at least make sure I'm prepared to see that type of question. That's good. Will I tell you all the types that I put in there? No, but like I haven't seen that much of you guys, so I'm going to try to be extra helpful here and narrow the scope down a little bit for you. Should you make sure you've practiced the problems in those 5-3 FRQ problems? Yes. Do you want to do another one of those? Just to remind us how to do that kind of thing? Okay. If you have your packet with you and want to pull it out and follow along, you can do that, or you can just kind of like watch what I'm doing. Either is okay. But I figure as long as we're doing stuff, let's do stuff. This is number 6, by the way. So for part A, it says g of x equals the integral from -4 to x of f of t dt. For each g of -1, g prime of -1, and then g double prime of -1, find the value or state that it does not exist. So g of -1 is the integral from -4 to -1, f of t dt. So it's that area, right? When I look at that, I see a trapezoid that's below the x-axis, so I'm going to make it negative. And then the area for my trapezoid is 1/2 times the bases, so B1 is like that side and B2 is that side. So that's -3, and then Yeah. And then -2. Oh, I shouldn't make them negative, though, because I already put the negative sign out front. And then the height is that, so that's 1, 2, 3. So what do I got? I got like -15/2 or something. Does that feel okay? You could break it up into triangles and plus rectangles, or however you wanted to do it is fine. That's, you know, if you didn't remember the area of a trapezoid, just chop it up into rectangles and squares and triangles that you can handle. That's fine, right? It's essentially how you build the trapezoid formula, is just breaking it into area, or, you know, 2 triangles and a rectangle and doing some grouping. So the derivative of this is going to be just f, right? So doing f of -1, well, that's just going to be -2. And the second derivative of g will then be the first derivative of f. But what do we notice is happening at -1 here? Corner. What does that mean? Yeah. Oh boy. So we ran into a corner there. I'm going to erase all these marks because I have a feeling I'm going to have to go back and look at this picture again, and it's going to get pretty busy. Part B says, for the function g defined in part A, find the x-coordinate of each point of inflection of the graph of g on the open interval from -4 to 3. Explain your reasoning. Inflection point is where the second derivative of g changes sign. So I know the second derivative of g is just the first derivative of f. And I'm going to be looking where that first derivative of f is equal to 0 or where it does not exist. So those are the 2 places where it can change sign. So if I look at f here, I notice that everywhere on f, the slope is not 0, right? There's no 0 slope spots on f. So my only options there for my inflection points are at x equals 1 and x equals -1, because that's the places where the derivative doesn't exist. Those are my candidates. But we still need to check to see if they're actually inflection points. We need the sign to change on f prime. So if I look at before -1, my slope is positive, right? Because it's going up. If I look after -1, my slope is positive. So -1 is not an inflection point. And then after +1, my slope is negative. So +1 is, -1 is not. And my explanation is that, you know, the sign of f prime changes at -1, but does not change at +1. And you could maybe explain more than that if you wanted to, but like that's essentially my explanation, is what I just talked through to you guys. Does that feel okay? Part C says, let h be the function, the integral of x to 3 of f of t dt. Find all values of x on the closed interval for which h of x is equal to 0. Okay. So One of them you should be able to name right away. 3. Everybody's good with why 3 is automatically one of them? Let's go back and look at our picture now and see if we can find any others. So remember, we're looking at areas under curve, right? So I'm starting here at 3. So all the way up until 2, my integral is going to be negative, right? So nothing can be equal to 0 between 3 and 2. After 2, we start becoming positive. So I need the spot where the area above the x-axis is the same as the area below the x-axis. Hey, that looks like it happens at 1, just looking at my eyes, right? Now you could calculate the area of both those triangles to make sure, but they are. So that's another one. Okay. So now if I go from 2, I know at 1, that h is 0. So let's keep going. So after that, I have that triangle. That's all positive. So nothing between 1 and 0 could give me h equal to 0. But after 0, we start getting negative again. And if I look at -1, it looks like, hey, that triangle now is the same above as it is below. That looks like that'll be another 0 at -1. Feel okay there? On what I'm looking at? And then after -1, well, all of those areas after again, we're 0 again at -1. And everywhere after is just going to be negative. So we're done, right? We found them all. Does that feel okay to you guys? Okay. And then D says, for the function h defined in part C, find all the intervals on which h is decreasing. Explain your reasoning. So h of x is going to be negative of this integral. Everybody's okay there? Because I flipped the bounds. Well, it's going to make the algebra a little bit simpler, but you could do it like without doing this. I'm just trying to show you like algebraically what I'm going to do. And then because we're looking about increasing and decreasing, I want to just take the derivative of that, which is just going to be negative f of t. And I want to look where negative f of t is less than 0, or if I divide both sides by negative, where f of t is greater than 0. Right? Should be okay. Is that what I did before? Let's look. Now I'm second guessing myself. Okay, no, I was right. Okay, good. And so the only place where f of t is greater than 0 is here, from 0 to 2. Does that feel okay? Much simpler to go that route than it is to try to like think about like, okay, where is the, like the integral going positive, like as I'm accumulating stuff, is it getting more stuff or less stuff? And like, this is so simple, right? To just think about it this way. And the reason I needed to make this critical first step is that the fundamental theorem of calculus part 1, that the derivative cancels out the integral, requires the x to be the upper bound. That's why I did that bound flip before I took the derivative, because I had to be careful about how I'm using that fundamental theorem of calculus part 1 to cancel out the integral. But as long as the variable is in the upper bound, you should be good to go. Now you might have to chain rule it too if the variable is like a function, if you have like an f of x in the upper bound rather than just like an x. But this one, it wasn't the case. Pretty simple. If you looked at it the right way, right? If you're like, I didn't know how to look at that, I did a whole bunch of stuff, I eventually ended up with the right thing, but boy, it took me a long time to get there. More often than not, like, there's usually a pretty simple, straightforward way to do these things, but you have to see it. You have to see it, right? That's the hard part. It's just getting used to like understanding what you can do and not do, so that the easy things are obvious. The hard ways are like, I don't want to do that. There's got to be a better way of doing it than that. But that just takes time and experience and just riding the struggle bus on stuff for a little, for some time, so you can figure out like why you don't want to do it the way that you're trying to do it. So it's like, oh, now I really understand, like if I go this route, it's going to get bad real quick. And there's got to be a better way of doing it. And you go back and look again, and it's like, now I got it. And like when you have those moments for yourself, you never forget them. Like that stuff is the best learning. That's the locked in stuff. If somebody shows you the trick, forget it. But when you find that you're for yourself, it's like, I'm never losing that. Yeah, Lucas, of course. That's probably about all I have for you guys. Paulo, you have something?
You don't have to do one, but can you just show us what like a Riemann like type of question would look like?
Yeah, so you'd get either like a graph or a table. So let's say it's just a table. So you get something like some kind of a table. Oh, whose birthday? Emily! Happy birthday. How old are you these days? Are you 17 or 18?
On Sunday.
On Sunday, though. Well, you're getting it early. Make sure you register to vote. Yes. All right. So if I want, like, say we want the right hand Riemann sum for this. So the right hand Riemann sum is going to be using these three rectangles, or the heights for those three rectangles. So the first rectangle, this is the width, and that's the height. The second rectangle, that's the width, and that's the height. The third rectangle, that's the width, and that's the height. So it's just going to be like 4 times 10 plus 3 times -2 plus 1 times 15. That's the idea. So I'll tell you, like, do it as a left hand or a right hand or a midpoint or a trapezoid or whatever, you know.
Left hand would just be your height would be 6 and 2.
Yeah.
What would the midpoint?
It'd be like the average of the, yep. Sure. Does that feel okay?
Yeah.
It's pretty easy. You just remember that, like, all I'm doing is building rectangles. Make sure you have the right heights. You know, that you're using the right end of the right value of the function for the height of your rectangle. It's pretty easy. You know, like as long as they're rectangles or whatever, you always have like one less rectangle than you do y coordinates. Is that the way I remember it? If it's a left hand, you start with the first one and you don't use the last one. If it's the right hand, you don't use the first one, but you do use the last one. And it's like pretty simple. Thing you have to be careful about is making sure that you're checking the widths, that whether they're uniform or not. Right here, the distance between the x's was not constant. Sometimes it could be. Doesn't have to be to do a Riemann sum. You know what I mean? But that's all there is to it. They should be easy, pretty quick. How's that? Feel okay? Elena? So you should, as far as area formulas for like geometric figures, yeah, you should know like square, rectangle, triangle, circle. I mean, you can use trapezoid, but if you know rectangle and triangle and you break the trapezoid up, you don't need the trapezoid formula. You could just break it into triangles and rectangles and stuff and be fine. But nothing past like what I would consider like middle school formulas that you've seen a bunch of times. You don't need anything wild. I would give it to you if you did. You know, like the related rates test, I think we all, you know, like when there's a volume of a cylinder or something, I think I put it in there so that like you couldn't just not be able to do the problem because you didn't have the formula memorized. You know what I mean? But those basic area formulas you should have, like square, rectangle, triangle, circle, should be locked in there pretty good. I suspect that you're like, okay, that's not a problem. I have all those.
So at the beginning, the summation stuff, and it's like the I.
So the only thing that you'd have to be able to do with that is to just convert between like between the notations. F of a plus minus a over n I times that. So like that's I think the relationship, don't quote me on that, I didn't look it up, but I think that's, so if I gave you like, if I gave you this side, could you come up with this one? This screams multiple choice question, by the way, right? Like this would not be something to do, when you looked at the test description, you didn't see this anywhere. This would only have been a multiple choice question. But that's all I would need from the summation stuff. Is just like, can you convert from an integral to a sum or from a sum back to an integral? I don't need you to calculate any of the sums or do any of the limits for the sums. That's beyond the scope of what we need to be able to do. Just using this definition is enough to kind of go back and forth to pick the right integral from the sum or the right sum from the integral. Is that what you're looking for?
Yeah.
Is that specific enough for you guys in terms of like what you need to know from those like first two chapters ish? I guess the first chapter you did Riemann stuff in there, or first section you did some Riemann stuff in there. I think that's where you built that idea out. So I have Riemann sum FRQ thing in there, but like that should be pretty easy. Jenny. Yeah, of course. What do you guys think? You have a decently clear picture of kind of what to be prepared for, I hope? How do you feel? This is time to tell your teacher the truth. How do we feel about what we've been doing? I've been here for 2 class days for this chapter. You need to tell me the truth because I haven't been here. I don't know. How are things going? Elena. What's up? That's what I'm trying to have a conversation about right now. I want to hear how you guys feel about this chapter. Well, so here's the thing. The date that we do things, especially in this class, doesn't matter to me, right? Like, if you're telling me that you want some more time to work on this, that's fine. We still need to continue to do other things. I can't just like jog in place. But that's okay if you're telling me, Mr. Gulick, I don't feel good about this right now. Like, I know I'm going to feel better on Monday after I spend a weekend doing this. But some more, like, Tuesday feels rushed. That's okay to tell me that. Like, if that's how you feel, just tell me. And this is me asking you, how are things going? And if it's bad, and I've seen you guys twice this chapter, that's not unfair of you to be like, yeah, like, I'm working, but like, I need to spend some time on this and then come back and talk some more. That's okay. Should we plan on not Tuesday? Okay. That's fine. You can tell me these things. It is okay. So just for clarity's sake, let's plan for Thursday, but we'll reassess on Tuesday. Thursday's not in stone either. Okay? Spend some time this weekend. Come back on Tuesday and really be able to talk to me about like what you feel good or bad about in detail, and we can help get you in a better spot. Okay?
Maybe on Kairos.
Okay.
I prefer to take it before.
You would prefer to do it before?
Yeah.
When do you leave for Kairos?
Tuesday.
I can have. Do you have a study hall or anything on Monday?
I was planning on taking another test Monday.
Okay.
If I take it in class, possibly.
Well, we don't meet on Monday.
I mean on Tuesday.
Oh, you leave after school on Tuesday?
Yeah.
I see. Yes, I can. You can go. I'll talk to Mr. Emmerich or whatever, but you'll check in with me.
What would we do Tuesday if we took it Thursday? We'll just start the next lesson.
Yeah, I'd probably see where everyone's at, touch base, kind of clear up whatever misconceptions, and then start in on the next section.
Okay.
Does that feel okay?
Yeah, that's fine.
Will you send me an email to remind me to do this so that I'm
Yeah.
prepared? Because I would love to believe that I'm going to remember this conversation, get right to it, but like, stuff happens. Thanks, Ryan.
I'm not messing on this, but I did it yesterday.
Okay, it might have been that you completed it after I'd already checked for it. Will you just send me an email and tell me to go back and look?
Yes.
And I'll make
I
sure.
did the same thing. And also the 5.3 one,
Did it?
I didn't see another one that came
Okay.
up.
Okay.
So
So just let's sit on that for a minute, because for me to make a new copy of it, I have to close the old one, and I think there's still, I don't know, I have to look to see if everyone's done it or not. But remind me again on Tuesday,
Okay.
and I'll for sure have it sorted
Okay.
and be ready to put something new for you to do.
All right.
And that's fine that like you tried to do it and just like,
it just took me out.
yeah.
All right.
I saw that looks like what happened on my end. I went back and looked and I said, okay, well, the new one is showing that you got it or zeroed on it for whatever reason. It probably something malfunctioned, thought the time had all elapsed or
Yeah.
something is my only guess. I don't know. But remind me again on Tuesday and we'll make sure
I
it's
will.
taken care of.
Thank you.
Yeah, no problem, Finn.
What are you doing on?
Do you give us the